Okay, so today we're going to apply our understanding of Chatelier's principle to an actual demonstration. I would normally obviously be getting you to do this demonstration, but that's not going to happen this year. So if you can find the investigation I put onto the classroom today, you can follow along with that. I will be flipping back and forth to this page from the other page in a bit. So we are going to do 3 equilibriums. This is the first equilibrium. It is a cobalt fluoride system in alcohol. So it's a little bit different. Excuse me, I have to grab a pen. It's a little bit different than what we've been talking about before because we've been talking about systems dissolved in substances dissolved in water or substances dissolved in gas. This one here, this little Al, that I can't circle because my pen doesn't want to work. This Al here, oh, for Pete's sake, means it's dissolved in alcohol. Now, I'm probably going to have to reorientate my board in a minute. And while I am reorientating my board, I want you to write the Kc expression for this guy. Now, these guys are dissolved in alcohol. It is a little bit different if they were aqueous. This is not liquid water. It's water dissolved in alcohol. Write the Kc expression for that. Okay, so the Kc expression for this guy is going to be our cobalt water ion in alcohol raised to the power of 1 times our chloride ion in alcohol raised to the power of 4. We leave energy out because we can't really measure error. We don't want to measure energy. And we have our cobalt fluoride 2 plus in alcohol. And in this case, we do include the water because it's not liquid water. It is a water that has been dissolved in another substance. If it was liquid water, we would not include it. But it's not liquid water. It is, as I said, water dissolved in a second solution. So, now what we have here, if you look at the camera, I don't know, hopefully this can be seen. This is our equilibrium mixture. It's got a purplish pink color to it. Okay, and we're going to be basing our predictions, or we want to basically see what's going to happen to the color when we do this. Now, I don't have these memorized. Off page 701, when you dissolve this cobalt chloride 2 plus in a alcohol solution, it's blue. And when you dissolve this cobalt water 2 plus in alcohol, it's pink. Now I got those colors off the chart on page 701. It's not that's something that we have to memorize. Now, here's the questions, and we're basically going to dump this in hot water, in cold water. So we're going to take this, put it in hot water, cold water, then we're going to add sodium chloride, and we're going to add sodium hydroxide. Or sorry, silver nitrate, I should say. Okay? So, the first thing that I'm going to do with this lab is add heat to it. Okay? So, when we look at this system, adding heat can be thought of as adding a product to the system. So adding a product to this system, we're going to speed up the reverse reaction in comparison to the forward reaction. It's going to shift to use up that heat. Okay? So we're going to shift to use up that heat. This will be a shift towards the reactants. Mixture and we should see a change in color with this. So if I compare to my equilibrium mixture, okay, this one here is significantly more blue than the mixture that is at room temperature right now. And it's a fairly significant change to this. So we can see that by adding heat, we do end up having this become more blue, shift towards the reactants, creating more of a blue compound. Any questions with that? Okay, so the next thing that I'm going to do is remove heat, i.e. place it in an ice bath. And we're going to go through the process the same way. Back up to my equation. I'm removing the energy as a product. We're cooling this down, removing energy. The system is going to want to fight that. What will happen is that will slow down the reverse reaction in comparison to the forward reaction. The reverse reaction requires heat to take place. You take some of that away, you're going to slow down that reverse reaction, causing a shift towards the products. Okay. So predict that we should have a system become more pink than the original. Now, I am just taking this straight out of an ice bath, and I'm going to put it on this paper or behind the paper. Now, the problem with this one is it's not as drastic as that blue one was. If I put these right next to each other, even my male eyes can see there's a lot more blue in the one on the left-hand side than there is in the mixture on the right-hand side. As I said, it's not as drastic because I only cooled it down maybe 15 degrees compared to heating the other one up about 80 degrees. But again, by going through the process there, removing heat, removing energy, going to shift it towards the products in that case. Where I want to go. Now, my next part of the experiment is going to be adding aqueous sodium chloride to the system. So everybody type in which way you think it's going to go, products or reactants. So we're adding sodium chloride to this system. Which way is it going to shift this system? Type into the okay. Anybody else got a tiebreaker between Rory and Sean? Okay, so let's take a look at the system. Here we have our equilibrium. By adding sodium chloride, what we're doing is actually adding sodium ions, which isn't part of this system, but we are adding chloride ions to this. So we're adding products to this. Okay? Since we're adding products, the system is going to fight you, and the reverse reaction will speed up in comparison to the forward reaction. And just like above, we can see that we're going to have a shift towards the reactant. It's the same arrow system in both. Okay. So I am going to add some sodium chloride to one of these containers. I may have to add a fair bit. I don't think I'm going to sodium hydroxide. I'm going to add that. I want to add this. The stuff that we're using here is 99% pure alcohol, so I'm hoping Mrs. Fraser doesn't walk in and get the wrong idea. Now, once again, okay, we see it's a lot cloudier, but I hope you can see that this one here does have a little bit more of a bluish tint than the one on the left. It's much more difficult to see uh, than what we had with the increase in temperature. But to my untrained eyes, I do see more of a blue color here. You might want to pin the screen that has my lab set up on your screen. Yeah, might give you a little bit more of a visual to that. Okay? Now, you can probably guess where we're going with the next one, but this is the one that causes us a lot of problems. We're going to add, you just check, make sure that this is what we're actually adding. I forgot the procedure. Yeah. So we're going to add silver nitrate. Now, the problem with this adding silver nitrate is there's no silver in here and there's no nitrate ions in here. What is adding silver nitrate going to do? I have to run back to my other computer to bring up my solubility chart. So when you see this where we don't have, there's no silver nitrate, there's no silver, there's no nitrate ions. Well, let's take a look at the solubility chart and see what adding silver ions do. So what we can see here is silver occurs in a couple places. There's one of them. That's the one I'm looking for. It is going to precipitate out, it's going to react with the chloride ions to precipitate that out. So what's going to happen here is the aqueous silver reacts with the aqueous chloride to produce silver chloride solid. Okay? So by adding the silver nitrate, we're going to remove these chloride ions and turn them into silver chloride. So what we're doing here is we're removing that. Okay, so use the solubility chart if it's not there. So removing the chloride ions, turning it, as I said, into silver chloride. What that removing that chloride ion is going to slow down the reverse reaction, not touch the forward reaction. And that creates a shift, creating more of the blue or more of the pink COH2O6 2+. Okay? So we're creating more product. We should see a pink color with this. And I will just do that right now. Again, this one we're going to have to look fairly hard for it. This is some silver nitrate. Now, one of the things that you can see, again, or at least I hope you can see, is in comparison to our sample, our original sample, it's got a lot cloudier for one thing. So that's that silver chloride ion or silver chloride solid being formed. And if I let it sit long enough, it will settle to the bottom, and you can, and again, I know it's hard to see, but there are silver or some solid white stuff at the bottom here. and most definitely is pinker than it was than this sample here. So our predictions as we went through, we can see the evidence of that predictions and see the evidence of that equilibrium shifting. Does anybody have any questions on that one? And I get people letting me know they're here by typing into the chat box. You have a question, Rory, or was that just you typing everything in?
No, I did actually have a question.
Okay.
For the one where I said it was going towards the products, so the first one, could you just re-explain that quickly?
So where we're adding the NaCl?
That's the one, yeah.
Okay, the NaCl. So if you think about what we have here, by adding NaCl in solution is actually the sodium ion and the chloride ion. We can ignore the sodium ion because it doesn't have anything to do here. So basically, I'm getting more of the Cl negative. Okay. So more of that Cl negative means more collisions between this guy and this guy. So that's going to speed up that forward reaction, and the reverse reaction is going to stay the same speed. Now, the other way of thinking about this is it's going to fight you. You added chloride. The system's going to fight that stress, so it's going to try to use up this chloride by going the opposite direction. Okay? So generally, if going back to this idea, it's going to fight you. It doesn't want to. So you added more chloride, it wants to go back to where it started. Now, how do I go back? I'm going to have to use up that chloride to create more of the reactants. Okay? We got a couple more examples of this. So we'll just, oh, I'm glad you're living, Alexis. We've got two more examples of this, and we'll go and we'll see if that helps, okay? Now, we have this system. This system is a indicator, bromothymol blue, with water. So it basically has a pH of 7 right now, slightly more than 7. But we've reached equilibrium where this equilibrium is green. Okay? And we have two stresses that we're going to apply to this. Adding HCl and adding NaOH. Okay? So let's talk about adding HCl. There's no HCl in that thing. Well, remember, HCl is a strong acid. It's one of our 6 strong acids. So when I add HCl to water, it's in solution, so I've added it to water. That's going to become hydronium ions and chloride ions. So what we're actually doing when we're adding the HCl to the water is we're adding the hydronium ions. Okay. So by adding the HCl, we're adding more. We are adding more products. The system wants to fight us with that adding. So since we're adding more HCl, or sorry, H3O plus, it wants to go back to where it started with. The only way it can do that is to shift the other direction. Okay? So the reverse reaction will speed up, the forward reaction will stay the same. We have a shift creating more yellow. HBB. Okay? So now again, these colors, we'll talk about how we decide to look at those as we get through the unit, but right now, okay, I have this saved, or I'm recording this. I'll put it on the classroom tonight. So we're creating more of the yellow HBB. So we should have the prediction in terms of color. The system should turn yellow. Well, let's see. I have, where is my hydrochloric acid? There it is. Okay, so the one on the right here is definitely much more yellow than the one on the left. There's no green at all on this one on the right-hand side, or right-hand side as I'm working with. Okay, so again, the prediction turned it yellow. Now this HBB, so equilibrium, is an indicator, like litmus paper is an indicator. And when HBB turns yellow, we know the pH is less than, I believe, about 6.0. Okay, so that's, again, this is how our indicators work. Now, adding NaOH. What does NaOH do? There's no NaOH anywhere in this. So, again, we have to think of this as where I'm going to beat this stupid machine. Sorry. Adding NaOH, well, what we're actually adding is the sodium ion and the hydroxide ion. Okay. Now, one of the things that we learned last year, I hope, I did talk about it, when you add hydroxide ions to hydronium ions, this reaction is one of the few acid-base reactions that we know is 100%. Okay, so for every hydroxide ion you add to that system, it's going to remove a hydronium ion. So what we're doing is removing the H3O plus. Okay, so removing the H3O plus, we're removing that. It's going to try to fight you on that removal. Okay, it wants to get back to where it started. So you've taken that H3O plus away. It wants to get back to approximately where it was to start with. That means we have to create more of that hydronium ion. Well, that's the system is going to shift towards the products to create that. And in terms of reactions, the reverse reaction will slow down. The forward reaction will stay the same. We have a shift toward the blue. So we should see a shift towards the blue HBB. That's, again, we were told that the BB plus, why I said negative. Yeah, I don't know why this says positive. This should say negative up here, but we should have a shift to the blue BB negative. Now let's see again. I need my HCl. Oops, I added the wrong thing. Perhaps I'll have to add a few more of these. Maybe not. So again, in comparison to the control sample that's in my left hand, you can definitely see that the sample turned blue. So again, our prediction is borne out by the experimental evidence. Okay? But I'm breaking this down according to what's happening. The Le Chatelier's principle states the system's going to fight you. That's at your very, very basic. If you can then start to talk about the forward and reverse reactions, which I find very, very useful, then that's the next step for this. Okay? And our third one is another guy here. Again, I'm just going to go to my page 701 because I can never remember these. This is a pale yellow. This has no color. And this is red. Okay? So the reason why we use this iron thiocyanate system is because of the different colors for this. We have three stresses we're going to put on this system. We're going to add Fe3 plus. We're going to add SCN negative, and we're going to add NaOH. Let me just check to make sure that I remember that correctly. Yes, I did. Okay. So what we're adding is FeNO3, we're adding SCN, but essentially we're adding Fe3 plus, SCN. And over here, what we're actually adding is, the important part is the NaOH. Now, both of these, iron and the SCN, iron 3 and the thiocyanate ion, they're both on the reactant. So these can be classified as adding a reactant. Okay, so we're increasing a reactant. System is going to want to fight that addition of that reactant. Okay? Doesn't matter which one of these I add, it's going to be the same process. It's going to try to reduce the addition. So it's going to try to get back to its original equilibrium concentration. And it's going to do that by shifting towards the product. So in terms of for both of these, we will have a forward reaction speed up, a reverse reaction stay the same, so we should have this system becoming more red in both cases. We have a nice bright yellow, nice bright yellow equilibrium. So if I add it's a little bit darker yellow in this case, but it's partially because what I've created it in, it's an older compound. Again, compared to the control sample in my left hand, most definitely became bright red. Well, much redder than the yellow sample. Now, that was my iron 3 solution. We should see a similar result adding my sodium or potassium thiocyanate. And, okay, well, this is why we do experiments. I don't see the same color. So that would be, not sure why that guy didn't work out to be the same. Okay. Now, experimental problems. I need to go back and see what's wrong with my experimental design. The one in my left hand has actually got a little bit more pale than what it should have. And I don't know why. Okay. So, again, bit of a problem. That's experiments. It happens. So, our thiocyanate did not work the same way. Well, something went wrong with the experiment on my end, not our prediction. And I need to add sodium hydroxide, right? Okay. So, well, it happens. Something went wrong with my system. Now, adding hydroxide again. What is adding hydroxide going to do? It's not part of the equilibrium at all. So that means probably have something to do with our solubility chart. Hydroxide ions are only soluble with group 1 ions and ammonia. That would mean most. Now, this solubility chart, we don't include too many, I don't think this solubility chart includes any polyatomic positive ions other than ammonia. So most importantly, what is in here is the Fe3+. Yes, we have the FeSN2+. It could also possibly be there, but this chart is generally only your common ionic compounds, and FeSCN2+ is not a common ionic compound. I know I'm possibly making this up, but so what happens, what we're going to be doing here is, again, removing the Fe3+. By adding that sodium hydroxide, that hydroxide is going to react with your Fe3+ to remove it. That system wants to get back to where it is. For this system to get back to where it is, it's going to shift to replace the iron 3. So we have a shift towards the reactants. To replace the Fe3+. Now what this means is it should become more yellow, less red. Now this is going to be hard to tell because they're both fairly yellow. What I should end up seeing here is this system. Go back to that one in a second because it actually does look like it's changed. So I'm going to add my sodium hydroxide to one of these. Add a fair bit of that. Shake it. Now, again, this is going to be very hard to see over the camera. What I'm starting to see in the one in my left hand is I'm starting to see some little bits of solid forming and going down to the bottom. Okay, so I do see some little bits of solid, so that is predicted as correct. And whether there is a slightly less yellow color to this one, very, very slight in my opinion. It's a little bit hard to see um, with the solid particles in there. So again, this is kind of inconclusive. Maybe one of you ladies with much more fine eyes for picking out color could see a different or see more of a difference. I see a little bit of one, but that may be just me talking, trying to feed my expected results into the actual results. Okay. Now let's just go back to that SCN one where we added the SCN negative. Now this is very, very hard to see. I guess maybe when I'm seeing it again, imposing my results that I expect upon the actual results, maybe I saw a bit more red in this when it was next to the red thing. So again, we have two inconclusive results. This one's, yeah. We have two inconclusive results with this experiment. Maybe if I add more sodium hydroxide to that, maybe I'll get a different red color. But that's what experiments are for. What happens when we do the experiment. Now we had 7 very conclusive experimental results on this and 2 not so conclusive, possibly because my eyes aren't good enough to pick out colors too much. That could be me. So, does anybody not have an understanding on how to use Le Chatelier's principle to do temperature or concentration changes? That didn't work. Okay. No, use that one here. I just want to find one more chemical as well. I might use that one. Okay, so let's talk about pressure, and then I'm going to give you a couple questions to do from this sheet as practice, and then we'll go over some stuff on Monday. So when we remember about pressure, we are looking at the molecule or the amount of gaseous molecules, moles, within a chemical reaction. The system will shift to minimize the pressure increase by shifting to the side with the least moles. And if you decrease the pressure, the system is going to shift to the side with the most moles. So let's talk about these two systems. We're going to decrease the volume and then we're going to increase the volume. Now we're going to do it to both of these separately. Let's talk about this first one here. We're going to decrease the volume in that system. Decreasing the volume is going to do what to the pressure? When we decrease the volume, we're going to increase the pressure. Now, the system's going to want to try to minimize that increase in pressure. Looking at this guy here, I've got 2 moles of gas, and I've got 2 moles of gas. There isn't a side that has less molecules on than the other. So what we would have for this one in equation 1, we would have no change. Okay? They both have equal moles of gas. We're not going to have a change. We would have the exact same thing if we tried to increase the volume, therefore decrease the pressure. No change as both sides have equal moles of gas. They can't, there's no shift that's going to minimize that pressure change. Now, for this guy here, if we increase the pressure, we have 2 moles of gas over here and 1 mole of gas over here. Decrease the volume, increase the pressure. System is going to shift to the side to minimize that pressure increase, which is the side with the least amount of moles. It's going to cause a shift towards the products. Because it has less molecules. What will we see? Brown color will disappear. Again, because we are shifting to the side that doesn't have the brown color on. Again, this would be about the only system that I would expect you to know the colors of anything right now, because we just use it so often. Maybe this one here, but I've never seen them say, never given a question that doesn't have the color here. If I was to decrease the pressure, it would be exact opposite, going the other way. I'm sure you're tired of hearing me talk. So I want you to go to the post lab. And I would like you to do 2 through 6 on the post lab as homework. And then I would like you to attempt number 1. So do 2 through 6. Before I go get a drink, does if anybody have any questions? If not, you may, let me just see if anything came up. Okay. If not, attempt those 6 questions on this. You don't have to print this out. Again, just attempt the questions. I'll go over them on Monday, and then we'll go from there. And if you didn't, just quickly type into the box. Keep the rest of you type in so it's to know you're still here. Rory, Sean, and Alexis are here. Jamie? Thanks, Jamie. Probably have to get my attention using the mic. I probably won't be at a computer, I don't think.
I don't know.
I'll open a bottle here and you can.
Are you doing experiments?
Yes.
Oh.
I just want to see how fast she's going to get here.
Oh, no. Ken's washed it.
Yeah, considering it's not only alcohol, it's 99% fruit alcohol. Well, with extra stuff added, but that's what its base is. I'll be back shortly. Oh, I gotta stop recording.